If you haven't watched the part 1, then you better go back and do that. Unless you know more than I think you know. Here is the Laplacian of the state function. Now you might say, why are we starting here? Well, this is a little bit of overlap from the hydrogen thing, and there's a few mistakes that were made, and that happens. So let's look at this thing. Okay, what is this big Y? Well, this is the angular function. This R is the radial function. And let's see, I think that covers everything. Oh, the L is a bunch of signs and stuff like that that gets lumped into the angular piece. And again, if you haven't watched the video part 1 of hydrogen energies, then that's not going to make a whole bunch of sense. Schrödinger equation. Here's the h bar squared 2m from the Hamiltonian. There's what we just described up here above. Let me put the cursor on so it makes you can see it a little bit better. There we go. And that should look good. Here are the eigenvalues, the energies, all that kind of stuff. Then what I'm going to do is spread this out a little bit and put the potential energy in here along with all this stuff that I just put together. Okay? There's the Y, there's the R, and I put the h bar squared over 2m. I put that all times this whole thing here, which should match up. There's the Laplacian, there's the Laplacian. And this, our old friend potential energy, and the Ry, which is the radial times the angular. So that's the whole function split into variables. What did it start out to be? It started out to be psi function. This guy right here. But now the psi is the Ry, radial and angular split apart. Talking through this because I want to make sure that everybody gets the idea straightened out in their head. Let's see where we go here. What's this step do? All it does is divide by Ry, divides by the whole function so that we have E isolated, and it's important to realize that E is a constant. Then to make sure that we let's see, what else happened there? Okay, 1 over Y, 1 over R. Okay, those are the effects of that. Now, because there's an R squared in the denominator here, it makes it a mix between the angular and the radial, and we don't want to do that. That's kind of the mistake I made earlier. So I'm going to multiply both sides times R squared. It gets rid of the R squared down here, the R squared down here, and it gets rid of one R here, and it actually puts an R up in the numerator, just as you see down here. And then we multiply both sides times negative 2m over h bar squared. Now, why would we do that? Why would we do that? Well, then it takes out this constant. That's a constant, mass. Planck's constant over 2 pi squared. 2 is a constant. So we're just going to multiply out that constant. And here, if we reorganize stuff, here's all the angular. Now see, that potential energy is brought down here in the radial because it has radial components. So all of this is radial. All of this only depends on the radius. So this is a function of the radius, and this is a function of the theta and phi, which are lumped together in the y function. And let's see, is it worth it to come over here and move that up? Okay, that's all we lost there. So now it's time to go on to page 2. This top line requires some retention from the last page. This is all of the radial stuff lumped together, and I've set that equal to 0 because the ER squared was on the other side, was on the right hand side. The angular part looks very clean and very short. That's because the angular stuff, which is quite involved, is all lumped into this quantity, into this angular momentum operator. And I guess that's all I have to say about that, except that, look at this. Lambda times h bar squared. Well, the h bar squared was under the L operator. Let's go back and see if we can see that real quick. See, it's under the L operator. So that's how that all occurred. See, this stuff all disappeared. We eliminated it and got it all kind of cutesy. So anyway, this h bar squared is still down here before we left. Now, what's the lambda all about? This is the separation constant that is in both sides of this. The lambda and the angular and the radial part of this. So this lambda is a constant, and it's the same lambda in both of these. Let's see what we got here. Multiplied by h bar squared times the radial part, that's required as part of it. And we've got ER squared, which used to be on the right-hand side, brought over here. And here's good old potential energy. And why did this turn into minus signs? Well, it was minus h bar squared. And look, the h bar squared over 2m disappeared. So h bar squared, what else did we do here? What's exciting? I don't see anything different here except that E gets put on the right-hand side. And where did the r squared go? Oh, we divided by r squared. So that put the r squared down in this portion, added there, and it put the r down here. There used to be an r up here, so you divide by r squared to cancel that, and you get an r down here. What changed here? Oh, this is a big deal. Look, I turned this from a first derivative of this mess, and I took it's a product, r squared and dr, so I took the first dr times the first derivative of 2r squared, which is 2r. R squared, using the exponent rule, becomes 2r with the first derivative, and now we take r squared times the derivative of dr over dr, which is the second derivative of r with respect to r. Capital R with respect to lowercase r. And this stayed the same. Now the r squared is no longer down here. How did that happen? Well, this constant is multiplied times this value. So the r squared created this scenario where it's 2 over r, multiplied the r squared, 1 over r squared times this thing, and it cleaned that up. My final step has a mistake in it. This should be h bar squared, not h. And then we put the lambda in there. So I think you can follow along with that. Oh, r times 1 over r, that just disappears. So we multiplied this top thing all by r. And that's how that came about. So this is Schrödinger equation. This is Schrödinger equation. That was crazy. You might want to watch that a second time just so that you can put it together. I know I have to watch my videos a lot so that I can keep track of where we're going. I was going to move on from here into the separation of the angular variables, which that's theta and phi, but I think I need a rest. I need to go ahead and publish this darn thing now so that I can collect my thoughts and get ready to twist your brain in half once again. So the goal is to get to the spherical harmonics. The spherical harmonics will tell us a lot about the shape of the orbitals, which is really what we need when we get into the molecules. So remember, we're going for the molecules. So we got to have all these what they call hydrogenic orbitals, because the hydrogen normally just has the 1s orbital, one little electron going around there, but if you get it to raise energy levels, it matches all these other s and p and d and f orbitals, and those can be very instructive in trying to understand how molecules interact. Where are we going? The nitrogenase problem and the iron molybdenum cofactor molecule.